Okay, we're live. So, we're not going to be doing set theory today. It's going to be cat theory. And I know how that sounds. We're not going to be talking about actual cats. It's short for category theory. Now, I don't know a whole lot about category theory myself, so I thought the way I'm going to do this is I'm just going to read a book about category theory, and then we're just gonna read along. When there's exercises, I'll try to solve them, and I'll try to, just read the book um on stream and see how that goes. So I'm learning, you're learning too, we're all learning here. Now, this is a book that you can buy and stuff. It's called Conceptual Mathematics by William Laver, or I don't know how to pronounce it. Now, is this copyright? Probably, but um, you know, I don't feel bad about pirating knowledge. Knowledge is something that you should be able to obtain for free, okay? You shouldn't be able to pay in order to just know something, know a fact about this world or this universe. You shouldn't be allowed to pay for that. That's just stupid. It's knowledge. Everyone has the right to that, and it shouldn't be blocked behind uh um a paywall or something like that. Okay. Um well, of course I pirate other things too, but that's not the issue here. The issue is, and the point is, I'm fine with pirating and showing you all knowledge even though it's technically illegal, because it is knowledge and everyone needs, or not needs, everyone just, well, needs to have access to it if they want to. That's my opinion. Alright, so category theory, I don't know a lot about it, so I can't give much of an introduction. What I can tell you though is that it's pretty difficult and it's also pretty useless. Well, if you're like, well, it's a pretty useless thing to study if you are, say, at an undergraduate level. So there's like a meme called like the undergrad category theorist meme, which is if this will load properly, which it's not doing that. Maybe we have to go here to get the actual image. What? Can I not, like, get superiority complex despite nothing to show for it? Burned out mathematical beauty receptors. Not even interested in the fields that category theory was invented to deal with. No free will, slave to abstraction. No longer creative, just thinks about categories 95% of the time. Can't solve a basic integral. Impaired problem solving. Can't calculate the homology of a simple CW complex. Don't let this PU stop before it's too late. Well, it's basically like, it's just like a rabbit hole that you can fall into, and unfortunately, I have fallen into it myself. Um, but this book is beginner friendly, so that's a plus, I guess. Anyway, let's begin reading. Um, and I'll just be reading the first part of the book because it's the introduction only, just because it's late for me anyway, and I need to go to sleep soon. So this will put me in a good sleeping mood, I'm sure. I think the first chapter or session, as they call it, is just like 7 pages long, so it'll be a breeze. Let's just make sure stream is still running and working fine. And I have a whiteboard over here just in case there's like something we need to do or visualize. Okay, okay. Um, Introduction. Our goal in this book is to explore the consequences of a new and fundamental insight about the nature of mathematics, which has led to better methods for understanding and using mathematical concepts. While the insight and methods are simple, they are not as familiar as they should be. They will require some effort to master, but you will be rewarded with a clarity of understanding that will be helpful in unraveling the mathematical aspect of any subject matter. So basically, it is something that can be used to explain or describe um, relationships between um, certain objects or structures in mathematics. So you could draw connections between different subject fields, right? From topology, and you could connect topology with Jesus, combinatronics. Wait, how do you say that? Jesus, combinatronics, right? Combinatorics. Jesus. Yeah, you could draw connections, and it can also help explain stuff, which is why a lot of people are drawn into it, but it's not as good as it seems, or so I've heard. The basic notion which underlies all the others is that of a category, a mathematical universe. There are many categories, each appropriate to a particular subject matter, and there are ways to pass from one category to another. So that's what I mean by what I said earlier. We will begin with an informal introduction to the notion and with some examples. The ingredients will be objects, maps, and composition of maps, as we will see. While this idea that mathematics involves different categories and their relationships has been implicit for centuries, it was not until 1945 that Eilenberg and MacLane, I think it's Ellen, probably, they're probably correct. Yeah. Gave explicit definitions of the basic notions. I thought they got the name wrong, but I think I'm the one that's wrong. In the groundbreaking paper, A General Theory of Natural Equivalences, synthesizing many decades of analysis of workings of mathematics and the relationship of its parts. Alright, Galileo and the Flight of a Bird. Let's begin with Galileo, 4 centuries ago, puzzling over the problem of motion. He wished to understand the precise motion of a thrown rock, or a water jet from a fountain. Everyone has observed the graceful parabolic arcs these follow, but the motion of a rock means more than its track. The motion involves for each instant the position of the rock at that instant. To record it requires a motion picture rather than a time exposure. We say the motion is a map from time to space. Right, so you give me a point in time, and I give you a point in space where the rock is at that given time. So it's just like a graph, like y-axis is where the rock is and x-axis is time. It's a map, like a function, yeah. So we can graph it and stuff, and that's what it would look like. It's familiar, right? So at this point in time, we have the rock is over here, this point is over here, this point is over here. Right? The flight of a bird as a map from time to space. Schematically, time, flight of bird, space. Right? So the flight of a bird is, or can be described as, a mapping between time and space. Makes sense, right? If someone asks you, what's the flight of the bird, you can just give them a mapping between time and space, and they can know, absolutely every detail that they want. They can choose a time, see where it gets mapped, and that's the location of the bird. And you can analyze and slide through the timer in order to analyze the movements with precision or whatever. Yeah, makes sense. You have no doubt heard the legend. Galileo dropped a heavy weight and a light feather, or a light weight. I thought it is a feather, right? That's how the story goes. From, I think, yeah, it's an anvil and a feather. I think those were the two objects. From the Leaning Tower of Pisa, surprising the onlookers when the weight hit the ground simultaneously. Oh, it can't be a feather because a feather has air resistance. Oh my god. Yeah, it's wrong then. The study of vertical motion of objects thrown straight up, thrown straight down, or simply dropped seems too special to shed much light on general motion. The track of a dropped rock is straight, as any child knows. However, the motion of a dropped rock is not quite so simple. It accelerates as it falls so that the last few feet of its fall takes less time than the first few. Yep, we all learned this in physics, don't we? Why had Galileo decided to concentrate his... I need to burp there for a moment. To concentrate his attention on this special question of vertical motion, the answer lies in a simple equation. Space equals plane times line. I guess that makes sense, because plane is 2D and line is 1D, and you get 3D. I think so. I think that's what they mean. Hold on. But it requires some explanation. Two new maps enter the picture. Imagine the sun directly overhead, and for each point in space, you'll get a shadow point on the horizontal plane. What? Okay, wait. So, there's a sun, and... Well, wait. The shadow map from space to the plane. The second map we need is best imagined by thinking of a vertical line, perhaps a pole stuck into the ground. For each point in space, there is a corresponding point on the line, the one at the same level as our point in space. Let's call this map level. What is space? What is space? Yeah, let's just see what the idea is. Okay, so there's a mapping between space and plane and space and line. One is called shadow, one is called level. Oh, okay. Okay, so it goes this way, but you can also bring it the other way around, right? If you know the position on the plane, and if you know, I guess the line is, oh, it represents like sort of the vertical height. So this is like the, I guess let's begin drawing. Hold on. Where is my pen? So you just have, you know, your usual... God, how do I draw 3D or while making it look good? So if you just have like this is a plot of land, and then you have like, let's just draw a tree here just to help with perception, you know, just so that. Right, and clouds here, just so we understand that this is 2D. Right, so if something is in space, let's say over here, right, then space, we can check their shadow to see where it gets mapped on the plane. So this point, if we take a look at its shadow, say this is a stone, for example, then its shadow gets mapped here. So this point in space gets mapped to this point in plane because it's on the 2D plane, right? Every point in space just gets mapped to a point in plane. right? So a 3D position becomes a 2D position if you look at its shadow. On the other hand, so that's one mapping, right? The conversion of 3D position or coordinates into a 2D coordinate by taking a look at its shadow. And another one where, let's say you have a pole over here, as they say, and then you just draw a line, a horizontal line between the pole and the object or whatever. And this point over here, right, that will be the line, right? So if you have another object over here, then that would get mapped over there. So a 3D position or coordinate gets mapped on to a 1D coordinate because all the points that gets mapped on to over here is just part of a 1D line, right? And it's also saying that to construct space, you can just have a point in the line and have a point in the plane, and you can combine those two together to get space. For example, right, we have this point in plane and this point in line. We can combine them together and we get this point in space. Cool, right? That's probably what it means, probably. Right. There is more though. Suppose you have a motion picture of the bird's shadow as it flies and a motion picture of its level. Perhaps there was a bird watcher climbing on our line, keeping always level with the bird, and you film the watcher. From these two motion pictures, you can reconstruct the entire flight of the bird. Yep. So, not only is a position in space reduced to a position in plane and one on the line, but also a motion in space is reduced to a motion in the plane and on the line. Yep, okay. Let's assemble the pieces from a motion or flight of a bird. Right, so time, flight of a bird, space. We get two simpler motions by composing the flight map with the shadow and level maps. From these three maps, right, ooh, and now space has disappeared from the picture. So what it's saying is, well, you can think of it like as a function, you know. So we have time. Let's say, right, this object was here in second 1, and then here second 2, here second 3, second 4, second 5, second 6, second 7. So that's the flight of like a bird going this way, right? So, right, that's time into space, right? Because these points here are points in space. Right, so it's basically a function. You put in 1, and then it says, well, the bird is here at time 1. Put in 2, the bird is here at time 2, so on and so forth. Right? It's saying that you can compose these maps. So for example, f1, you get this point, right? And what you can do is you can apply another function, right? The function that converts space into line, for example. Let's say g, right? f1 is the position of the bird at time 1. So that's a point in space. And then you map it again. You compose it again. And now you get this. Right? So g of f of 1 is this point on the 1D line. Right? And if you just keep going like this, then what you'll get is level of flight of bird, right? how high is the bird at a given point in time, right? This is GFF1, this is GFF2, GFF3, GFF4, and so on and so forth. And it's telling you that the bird is like 100 meters above, and now it's 90 meters, now it's 80, now it's 70, and so on. And you can do a similar thing for the plane as well. And you get that by composing these two maps as we've done, right? We converted time into space with the function f, right? And that represents the position of the bird at a given point in time. And then we did an extra step, right? Converted time into space, and then we did an extra step. We converted space into line, or, well, height is more better way to say it. Right, so we converted time into space and space into height, and then we get this thing instead. Right, and then now we don't have to deal with space at all. Right, we removed the middleman here between our compositions, so that's interesting. Yep. In fact, if the motions of the shadow and the level are continuous, so that the shadow does not suddenly disappear from one place and instantaneously reappear in another, the motion of the bird will be continuous too. Okay. This discovery enabled Galileo to reduce the study of motion to the specialized cases of horizontal and vertical motion. It would take us too far from our main point to describe here the beautiful experiments he designed to study these. And what he discovered, but I urge you to read about them. Does it seem reasonable to express this relationship of space to the plane and line given by two maps? Yeah, by the equation space equals plane x line. What do these maps have to do with multiplication? It may be helpful to look at some other examples. Other examples of multiplication of objects. Multiplication often appears in the guise of independent choices. Here is an example. Some restaurants have a list of options for the first course and another list for the second course. A meal involves one item from each dish. The first course is soup, pasta, salad. Second course is steak, veal, chicken, fish. So one possible meal is soup, then chicken, but veal, then steak is not allowed. Right? Makes sense so far? So, yep, okay. Fill in the other meals yourself. Notice, fill in the other meals yourself. Also, this is like an exercise. Well, it'll be pasta veal, pasta chicken, pasta fish, salad steak, salad veal, salad chicken, salad fish. Pretty sure everyone can understand that. Fill in the other meals yourself. Notice the analogy with Galileo's diagram, right? So from meals, you can convert meals into second courses with like a function or something. So let's say your input is soup steak, right? That's a meal. You can convert it into a second course, right? So f, let's say the function that brings meal into second courses is f. That's the mapping, that's the function that converts meals into second courses. So f of soup steak is just steak, because you only obtain the second course. Just like over here, this is a 3D coordinate, like x, y, z. And here is just a 1D coordinate, which is z, right? We only extract the part that we need, right? This is x, y, and up here we have z. So we just extract the z coordinate because that coordinate represents height. We don't care about the rest of them. Just like over here. This is like it has multiple information in it, right? We just extract one. The one that, well, is pertinent to, the second course part of the thing. Right. This scheme with 3 objects and 2 maps or processes is the right picture of multiplication of objects, and it applies to a surprising variety of situations. The idea of multiplication is the same in all cases. Take, for example, a segment and a disk from geometry, we can multiply these two and the result is a cylinder. I'm not referring to the fact that the volume of a cylinder is obtained by multiplying the area of the disk by the length of the segment. The cylinder itself is the product segment times disk, because again there are two processes or projections that take us from cylinder to the segment and to the disk, in complete analogy with the previous examples. So a segment in geometry, I think it's just a line that is not infinite. I think that's the definition of a segment. So just a line that's not infinite. And we have a disk. And we can multiply these two to get a cylinder. So I think how this works is, so what I'm getting at is that multiplication puts two pieces of information together, right? Like we can put the information of like where an object's shadow is and an object's height is. We can bring those two information together and we can obtain where that object is in space, right? If you know a person's z level and if you know their person's xy level, then you know exactly where they are in space, right? You just have to piece those informations together, right? If you know what the person chose for the second course and if you know what the person chose for the first course, you can bring them together to see what their meal is. Okay, makes sense. So over here is more abstract, right? If you have a point on the cylinder and a point on the line, then you can combine these to obtain a point over here. And if you have this point, the same point, and another point at the bottom over here, then that's if I draw like this to represent that this is like the back part of it, I don't know, then that would be like somewhere here, right? So you can combine the coordinates or the points on a disk and you can combine them with the coordinates on a segment, and the result is, well, you get coordinates of points in the cylinder, right? If you just run through all the combinations here, you'll eventually like fill in the shape of a cylinder, right? So all the points on this thing cross all the points on here, every single combination of which, if we just keep trying different combinations, say this and this, this and this, you get this, this. We fill the whole thing up, we get the shape of a cylinder, right? Just by combining these two pieces of information together and trying all the possible combinations, you'll construct a cylinder, right? If you run through all the points, we'll fill in everything in the disk, we'll fill in everything in the line segment, and the result of those combinations together will fill in the entire cylinder as well. So that's how a disk and a segment constructs a cylinder, just like how a first course and a second course constructs what is a meal. Pretty cool. They have like the thing here, right? A diagram here, so I didn't need to draw. Right, every point in the cylinder has a corresponding level point on the segment and a corresponding shadow point in the disk, and if you know the shadow and level points, you can find the point in the cylinder to which they correspond. As before, the motion of a fly trapped in the cylinder is determined by the motion of its level point in the segment and the motion of its shadow point in the disk. Right, an example from logic will suggest a connection between multiplication and the word and from a sentence of the form A and B. For example, John is sick and Mary is sick. We can deduce A and we can deduce B. Right? This is the part I'm interested in because, well, it's logic, and I've made like a bunch of videos on logic on the main channel, and I also have them on this channel as well. Right, we have a statement over here, and from that we can, extract bits of information from it. I think the point is clear already. We've seen a bunch of examples, so I'm not going to explain this one. But more than that, to deduce the single sentence John is sick and Mary is sick from some other sentence C is the same as deducing each of the two sentences from C. Wait, let me read that again. To deduce the single sentence John is sick and Mary is sick from some other sentence C is the same as deducing each of the two sentences from C. In other words, the two deductions CA and CB amount to one deduction CA and B. Huh. That's the end of the first chapter. Alright. We're almost done here. I just need to try to understand what this is trying to say over here. I get that. So, if like from a statement C, you're able to extract that Mary is sick, and you're also able to extract from that John is sick, then that's the same thing as extracting, C, extracting A and B from C. Right? Okay. So if we extract this from this, right? So C we can extract A and B from, and A and B we can extract A and B from as well. Okay, let's, I think I get it. One last picture, perhaps the simplest of all, hints at the relation to multiplication of numbers. Right. This one's more complicated though, because yeah, I'm just thinking here because, like, obviously multiplication, yeah, you can think of it as like combining two things from one another. In this case, well, these are explicit objects, but this would be like this, because 6 is a number, 3 is a number, 2 is a number, right? Before we were dealing with different types of objects. For example, a 3D space, this is a 3D, this is 2D, this is 1D, but over here it's just 6, 3, and 2, which are all numbers, they're all the same type of object. So that's what it would look like. But the problem is, right, if we have 6 over here, we can't extract like the information specifically, or I don't know how to say this. We can't extract the information in a unique way. For example, 6 we can extract, 3 and 2 out of, but it can also be the case that we get 6 and 1 again, right? Or 4 and what's 6 over 4, which is 3 halves. So 1.5, right? Or you could get 4 and 1.5. So whereas, for example, if you have a 3D point, XYZ, then you can only ever extract like there's only one answer or like one way to extract information from here into information from here. Whereas over here you have multiple ways of extracting information. So I think this is like there are different kinds of category. Like this is like one kind of category, one where like the extraction is unique, whereas over here the extraction is not necessarily unique. You can extract them in multiple different valid ways. So I think that's probably what it's getting at. Right, there are different ways you can arrange this. Right, for example, they show this diagram, but it can also be like this instead. And then you'll have like 2 here and then 3 here. Right, or just 6, 1. Like the shadow height, the height of this is 1, the shadow of this is 6. The height of this is 3, the shadow of it is 2. But they're both 6. Right, so there are different ways that you can construct this map. I hope these pictures seem suggestive to you. Our goal is to learn to use them as precise instruments of understanding and reasoning, not merely as intuitive guides. Let's do some of the examples. Find other examples of combining two objects to get a third. Which of them seem to fit our pattern? That is, for which of them does the third object seem to have maps to the two you began with? Start by thinking of real-life problems for which multiplication of numbers is needed to calculate the solution, but not all examples are related to multiplication of numbers. Well, which of them does the third object seem to have maps to the two you began with? I don't know. Cooking is an example that's used a lot in like these kinds of things because I've seen cooking used a lot. So it's like, I don't know, like you get eggs. Like this will not be a 2 thing. It'll be like a 3. Like they're just dealing with 2 things combining into another thing, but theoretically you can have 3, 4, maybe even an infinite amount. But like if cooking, you get eggs, flour, sugar. You could get cake, for example. And from cake, you can tell that it is made out of eggs, made out of flour, and made out of sugar. And milk, maybe. There are different kinds of cakes and types of cakes. But yeah, that's sort of the idea of it. The part of Galileo's work which we discussed is really concerned with only a small portion of space. Say the immediate neighborhood of the Tower of Pisa. Since the ground might be uneven, what could be meant by saying that the 2 points are at the same level? Alright, try to describe an experiment for deciding whether two nearby points are at the same level without using height. Distance from an imaginary plane of reference. Try to use the most elementary tools possible. I don't even understand the question, man. So I get that the ground might be uneven, so that, like, the plane is not actually a plane. Man, I don't know, like use a GPS or something? I don't know. Um, so yeah, if like there's hilly terrain or something, then like if you're mapping it here, then that's not an accurate representation because the terrain is bumpy. It's not an accurate representation of the XY plane, which I get. So it says, how do you solve that? Well, huh. Man, I don't know. What do you mean same level? Yeah, I'm just gonna skip this. It's not like, I don't think it's relevant anyway. Let's just read like the first, like the introductory part of this new chapter here, just to get a taste of what we're getting at. Um, hey, it's sets. We were studying set theory. A category of sets. A map of sets is a process for getting from one set to another. We investigate the composition of maps, following one process by a second process, and find that the algebra of composition of maps resembles the algebra of multiplication of numbers, but its interpretation is much richer. Okay. Before giving a precise definition of a category, we should become familiar with one example, the category of finite sets and maps. An object in this category is a finite set or collection. Here are some examples. The set of all students in the class is one object. The set of all desks in the classroom is another. The set of all 26 letters in our alphabet is another. So I talked about set theory before, so we can sort of skim through the details here. Probably familiar with some notation for finite sets. Yep. Blah 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 blah. Yep. Where dot represents each element, and we then feel free to leave off the labels when, for one reason or another, they are temporarily irrelevant to the discussion, and picture this set as like this. Such a picture, label or not, is called an internal diagram of the set. Right, we haven't talked about functions yet in my set theory videos, but we will at some point in time. A map in this category consists of three things, right? A set, a codomain, a set A called the domain of the map, a set B called the codomain of the map, a rule assigning to each element A in the domain and element B in the codomain. This B is denoted by F circ A, or sometimes F bracket A bracket read F of A. Other words for map or function, transformation, operator, arrow, and morphism. An example will probably make it clearer. Let A equals John, Mary, Sam, and let B equal eggs, oatmeal, toast, coffee, and let F is assigned to each person his or her favorite breakfast. Then here is a picture of the situation called the internal diagram of the map. So it seems pretty natural so far, right? I mean, you're all familiar with functions and everything. Right, yeah, this is the one condition for a set or for a function. One object cannot map into two or more different objects. So if you have one object in the domain, it can only be mapped to one object in the codomain. You can't have John mapping to eggs and John mapping to toast, because you can't have two favorite things, because favorite is like the most favorite, so you only have one favorite thing. If you have two, then you have to pick either one of them as your favorite, and the second one will be your your second favorite thing, not your first favorite thing, right? Um, yeah. But objects in the codomain can have multiple arriving arrows, right? It's possible for multiple people to enjoy the same thing, right? So that's the condition for a function, right? One object maps to one thing. You can't have an object mapping into multiple things. The important thing is for each dot in the domain we have exactly one arrow leaving, and the arrow arrives at some dot in the codomain, right? Nothing in the discussion. Oh, also, everything in the domain must be mapped. I don't know if that will be mentioned at some point here, but yeah, for each dot in the domain, right? So each dot must have a map or an arrow leaving. If there is no arrow over here from Mary to coffee, if you just erase that arrow, then this will no longer be a function. Nothing in the discussion above is intended to exclude the possibility that A and B, the domain and codomain of the map, could be the same set. Right, here's an internal diagram of such a map G. Right, we could have a set mapping into itself. Many 1950s movie plots are based on this diagram. Oh, I get the joke. It's a love triangle. Two guys like a girl, but the girl only likes one guy. Hey. A map in which the domain and codomain are the same object is called an endomap. Why? What does the prefix endo mean? I don't study Latin. I don't know. For endomaps, only an alternative form. For endomaps only, an alternative form of internal diagram is available. Here it is for the endomap above. Right, so you can draw it this way if you want to, because it's the same set. Makes sense. This is the identity map. Identity map. Alright, let's call it for here. We had like a taster of what we're going through next. How many chapters or no pages is this set theory gonna be? This is a big book, by the way. Really big book. Bruh. Okay. That's 7, 8 pages of like the first part over here. Going into 21. Before we begin session 2. Where did we stop? Here. 15. That's like 6 more pages left. Should we go all the way? I mean, fine, it's just 6 pages. Alright, so we have the identity map. It's just the map that maps an object into the set to the same object. Cool. Sometimes we need a scheme to keep track of the domain and codomain without indicating in the picture all the details of the map. Then we can use just a letter to stand for each object and a single arrow for each map. Here are the external diagrams corresponding to the last 5 internal diagrams. What? Oh, yeah. So G over here is this one, right? This one here, right? Yeah. So you can draw it A arrow G, but since A is, well, the same thing as A, it's actually just an arrow mapping from itself. So these things are just the same thing represented in 2 different ways, just like how this over here is represented in 2 different ways, the same thing. External diagrams are especially helpful. Hold on, I need water. External diagrams are especially helpful when there are several objects and maps to be discussed, or when some of the exact details of the maps are temporarily irrelevant. The final basic ingredient, which is what lends all the dynamics to the notion of category, is composition of maps, by which 2 maps are combined to obtain a 3rd map. Here's an example. Right, this is pretty self-explanatory. If G maps is the favorite person map and F is the favorite food map, then you can just compose them together to create a new map, right? So we have John going to Mary and Mary going to coffee is like the G associates this with this and F associates this with this. We get a new mapping, a new association, right? That's just like that just consists of the start point of the composition and the end point of the composition. So our start point is John and our end point is coffee. So that's going to be our new arrow. So, and our new composition over here, right? We get 1 map G and F, and now we combine those 2 to get a new map. Now this map, it associates John with coffee, as you can see over here. That's because it follows along G and it follows along F. The start point is John and the end point is coffee. So that's how it decides, how to map the object in the domain into the object in the codomain. Right? It follows this, it just follows the composition in order to achieve that. Right. So this has a representation. It's, well, if you have G as favorite person, F as favorite food, then G of F, right? If you combine G and F together, that new function or that new mapping will be the mapping that is favorite food of favorite person, right? So the favorite food of John's favorite person is coffee. And the favorite food of Mary's favorite person is eggs. So we know that Mary likes the person that likes eggs, and John likes the person that likes coffee. Sam also likes the person that likes coffee. Of course, we know that that person is Mary, and stuff like that, Yeah, what should each person serve for breakfast to his or her favorite person? You could also framework it that way. I think that's much better. Of course, they wrote the book, so they had time to come up with a good example, unlike me. So f of g represents what they should cook for their favorite person. Obviously, John is going to make coffee for Mary. Sam is also going to make coffee for Mary, and stuff like that. F following G, or f of G, the favorite yeah, that's what I said. Literally, like, the favorite breakfast of the favorite person of John is coffee. Let's sum up. If we have two maps, f and g, and if the domain of f is the same as the... Oh, yeah. So... Right, so G maps A into A, right? So if we want to compose two maps together, then the codomain, right, of G, which is... So we have... Hold on. A, B, right? This is G, this is F, right? This is the codomain of G. This is the domain of F. Right? The codomain of G must be the same as the codomain of F. Otherwise, it won't work. For obvious reasons, right? If we have A taking, say, numbers into people, right? Like in like a classroom, for example, who's the first student? Who's the second student? Who's the third student? And stuff like that. And then you can have people into, food, favorite food. That makes sense. That's G and this F. But if F takes food into, I don't know, ingredients, right? From food you can gather, like, or obtain, like, or have an idea of what ingredients make up the food, then you can't compose these two maps together. Because like, a number goes into a person, and then if you want to compose that map with another thing, then you need an arrow from a person to something else. But F does not have that information. F has the information, or the arrows, which go from food to ingredients, but it doesn't have arrows that go from person to something. And if you don't have that information, then you can't create a composition. That makes sense. Right, the domain of F needs to be the same as the codomain of G. We will soon be considering an analogy between composition of maps and multiplication of numbers. This analogy should not be confused with the analogy in section 1 between multiplication of objects and multiplication of numbers. That's all. These are the basic ingredients we need to have a category or a mathematical universe. Data for a category. We need objects. Okay. We need maps. We need identity maps. One per object. So each object has an identity map. A has an identity map. B needs an identity map. C needs an identity map, and so on and so forth. And we can compose maps together, right? And these data must fit together nicely as follows. Rules for a category. Identity laws. If you compose identity with G, then that's the same thing as G. Right? I feel like that's obvious, right? Because the identity map does nothing. It transfers the same object to the same object. And it goes the other way around as well, right? And the order at which you perform the mapping, right? If you map G and F first together, and then if you map G and H together, then that's the same thing, right? These should make sense, right? You can see this goes to here, goes to here. this goes to here, goes to here. So the mapping will be this goes to here, this goes to here. Yep. I don't think we need to see all of that. Ooh, exercises. Damn, okay. So I guess we'll do some of the exercises. We'll not do every single exercise. But we'll do some of them definitely, and we'll do them next time, because I need to sleep now. Okay, see you next time then.